Okay, for this video, we'll be going through general wave properties, success criteria A. Okay, so although this has really, success criteria A was actually covered right at the start, but there was this term called wavefront, which I have not gone through until now. Okay, so let's take a look. Now, state what is meant by the term wavefront. So this is the definition that you need to memorize. Okay, so I find that I need to actually go through other concepts first before I come to wavefront, right? So wavefront is defined as the imaginary line on a wave that joins all adjacent points that are in phase. I hope you still remember what is the meaning of in phase. Basically, it is the same displacement, okay, and same velocity. And if you know that velocity is actually a vector quantity, it would cover same speed and same direction, right? Okay, so straight dipole will actually produce plane wavefront. Plane just means straight, okay, like that. While a spherical dipole will produce circular. So this is more common when you throw a rock into a pond. Now, this is important. The distance from one wavefront to the next wavefront is the wavelength. Okay, so I will need you to write this down. You will actually need to count the gaps, count the number of gaps, because every gap is one wavelength. From one wavefront to the next wavefront, we don't count the number of wavefront, we count the gaps. Okay, let's use an example to go through what we have just learned. Ripple tank is used to create circular waves as shown in the diagram below. The dipole creates the waves at a frequency of 20 Hz. So again, map it to the physical quantity. So it's F. So now I know F equals to 20 Hz. And the speed is 20 cm per second. So this is the V. So if I have V equals to F lambda, out of these two, I know my V, I know my F. I can actually calculate my lambda. Okay, but they did not ask us to do so. They asked us to find the diameter of the largest circle X. So this is the source of the vibration. So from here to here is actually the radius, right? It's actually the radius. They're asking for diameter. That means it's 2 times radius. Now, let's count the gap. There's one gap. This is one wavefront. Second, third, fourth, fifth. Okay, but I don't care about the wavefront. I just count the number of gaps. From the center of the vibration, which is here, I count there's one gap. Let me zoom in. One gap, 3, 4, and 5 gaps. So from the source of vibration to X is actually a radius, right, of the circle. And there were 5 gaps. Okay, 5 gaps means 5 wavelength. Okay, now with this formula, V equals to F lambda, 20 equals to F times 20. Sorry, frequency is 20, the V is 20, F is 20. I can find the wavelength. The wavelength is actually 1 cm, right? So I have 5 gaps, 5 wavelength. So 5 wavelength will be a value of 5 cm. Okay, and this is the radius. Therefore, the diameter will be 2 times 5 equals to 10 cm. Okay, so this is how we apply counting the gaps. Let's go through one more example. A wave generator which makes 10 oscillations a second. So this is important. 10 oscillations a second means there are 10 complete waves. That means the frequency is 10 Hertz. Okay, that means in 1 second there are 10 complete oscillations. It's used to produce waves in a ripple tank. Now, which of following shows the correct values of frequency, wavelength, and speed? So again, map all the quantities, the physics quantities. So I have already my frequency, which is 10 Hertz, right? So answer is either C or D. Now wavelength. This is the source, right? And this 12 cm spans from here to here. Let's count the number of gaps. 1 gap, 2 gap, 3 gap, 4 gap. So I have 4 gaps. That means, and they have this length of 12 cm. And each gap is actually a wavelength. So I have 4 wavelength is equals to 12 cm. One wavelength will be 3 cm. Okay, so let's just check the final answer. V equals to F lambda. This is wave speed, right? I have my frequency, which is 10. I have my wavelength, which is 3. So I'll get 30 cm per second. So answer is C. Simple. Okay, now the diagram shows the change of direction experienced by water waves passing from one depth to another. So there's a change in depth. There's a change in depth. Okay, so if there's a change in depth, you apply your SSSS. What is SSSS again? Same frequency. Okay, shallower. That means it goes from deeper to shallower. So when it goes from deeper to shallower, we will have a shorter wavelength and slower speed. Okay, so where do we have shallower? So if I look at Y and X, right, here, this is the wavelength. The wavelength is actually larger. Wavelength of X is larger than wavelength at Y, right? So here, the wavelength is shorter at Y. That means it's going to be slower at Y. That means it's going to be shallower at Y. So the waves in depth Y have C and D is straight away wrong, right? Because the frequency will not change, right? Due to this. Okay. Where does the wave in depth Y will actually be slower, a lower velocity. So B. Simple. Okay, A4. Waves travel more slowly on the surface of water when the water is shallow. So actually, sometimes the question tells you the SSSS, right? So shallower, slower. A girl makes an oscillatory motion by dipping her finger up and down into a pool at X. Diagram shows the wavefront. Where is it likely to be the most shallower? SSSS, shorter. So A will be most shallow. Correct? Because the wavelength is the shortest. SSSS. Okay, A5, figure below shows circular wave fronts produced at the center of a circular ripple tank. So this is where the vibration is. And we take note that the wavelength is 8 cm is already listed over here. So two corks A and B float on the water in the ripple tank. They move up and down on the surface. The wavelength of the wave is 8 cm. They tell us this. Now they give us this DT graph. So again, what can we get from DT graph? We can get amplitude. So very quickly, what's the amplitude? It's from rest position to crest. So it is plus 2 mm. Okay, so the amplitude A we can get from the y-axis. It is 2 mm. Oh, okay, 2 mm. Yeah. The horizontal distance between A and B is half the wavelength of the wave, right? On the figure above, sketch a graph to show how the displacement of B varies with time. So if A is up, B must be down, because A is actually crest, right? This position where the other wavefront is also a crest. Why is it that only the wavefronts, why is it that the crests are the wavefront? It's because the crest is on top. It's at the highest point. So they actually reflect more light, right? You think about it, it reflects more light. So we are actually able to see all these lines because they are at the top, they reflect more light. So B is actually at the trough, right? So if A is at crest, B must be at the trough. So I will sketch B to be like that. Okay? Why? Because they have the same amplitude. They have the same displacement. But one is positive, the other one is negative. They both have zero velocity, right? So it looks like that. Now determine the frequency of the wave. And because this is a DT graph, we can actually get from the x-axis the period, which is the time taken to complete one wave. So let me remove the red color. Let's focus on A's profile. So the time taken to complete one wave, it is 0.50 seconds. So the period is 0.50 seconds. What did they ask us to find? They asked us to find the frequency. So apply this formula, f equals to 1 over t equals to 1 over 0.50 equals to 2 hertz. Okay, so we are done. Now the distance between the center of the ripple tank and the edge is 40 cm. So from here, okay, so this one looks like the previous question. So from here to here, right, take note, the center to the edge is 40 cm. It's 40 cm. Okay, so how many gaps are there? 1, 2, 3, 4. No, because they will tell us that the wavelength is 8. So there is actually one more, right? Because they say that distance between center to the edge is 40 cm. So if the wavelength is 8 cm, I have 1, 2, 3, 4. 4 wavelength equals to 4 times 8. It is 32. Okay, that means I'm actually able to have one more wavelength here, one more wavefront, to have one more wavelength. So 5 gaps, 5 times wavelength of 8, that will give me 40 cm. So determine the time taken by a wavefront to travel from the center of the tank to the edge. Okay, now we already have the wave speed, do we? But actually, do we need that? What's the time taken to complete one wave? It is t is equals to 0.5 seconds, right? The distance is actually 40 cm. Okay? And okay, the time taken to complete one wave is 0.5 seconds. And there are a total of 5 waves. So it will be times 5. So it will be 2.5 seconds. Okay? So that is what I think is the answer. But I'm not very convinced, so I'm going to do another method. Determine the time taken by a wavefront to travel from the center of the tank to the edge. Okay, so maybe I calculate out the wave speed. V equals F lambda. I have the frequency, it's 2 hertz. I have the wavelength, it is 8 cm. So the wave speed is actually 16 cm per second. Now, to calculate the time taken to travel a distance of 40 cm, right? Because it's going to go from the center of the vibration, which is here, all the way to the edge, right? All the way to the edge. So I will need to use distance equals to speed times time. I have distance 40, the speed is 16, my time should be 2.5 seconds. Okay, so you can use either method.